This is segment 3 of the Module 8 lecture. Here we introduce another concept, which is the type of errors in experimentation. So when we make a decision about a null hypothesis using a sample statistic, we may incur an error in our decision, and just because the population parameter is unknown. This table summarizes the errors that we can commit when making a decision about a null hypothesis. So here on the left side of that table, we have the experimenter's decision based on the sample statistic. And he can either do not reject the null hypothesis or can reject the null hypothesis. On the right side of the table, we have the actual situation. So we have the situation where the null hypothesis is true, or when the null hypothesis is false. All right, let's look at the consequences of each of these decisions. Let's say that the experimenter decides not to reject the null hypothesis. So if the null hypothesis is true, well, he or she made the correct decision. But if the null hypothesis is false, then the experimenter has incurred in what we call the type 2 error. So he did not reject, or she did not reject, a false null hypothesis. Now, let's look at the other decision. Let's say that the experimenter decides to reject the null hypothesis based on the value of the sample statistic. So if the null hypothesis is true, well, the experimenter has just incurred that in the type 1 error, because the person rejected a true null hypothesis. Now, if the null hypothesis is false, then by rejecting the null hypothesis, the experimenter has made the correct decision. So these are the two possible mistakes that we can make when we reject when we decide to reject or not to reject the null hypothesis. Now, each of these errors has a probability, or probabilities assigned to each of these errors. So alpha is the probability of the type 1 error, and that's a probability of rejecting the null hypothesis given that the null hypothesis is true. This is called the significance level or the risk level, and this is a complement of the confidence level. This is what we encounter when we were calculating confidence intervals. Then beta is the probability of the type 2 error. So that's a probability of not rejecting the null hypothesis when the null hypothesis is false. And the complement, 1 minus beta, is the probability of not making the type 2 error, and that's called the power of the test. This criteria, the power of the test, is what is used to calculate sample size. Unfortunately, in our course, we will not go that far. All right, I included these mnemonics. I hope they're helpful to you. For example, this ART mnemonic, the A represents the alpha probability, R to reject, and T a true null hypothesis. And for the type 2 error, a mnemonic that has been useful to me is called BAF. And B is for beta probability, A for accept, and F for a false null hypothesis. Of course, the word accept, we don't use it in the context of hypothesis testing. And the reason for that is given in this example. So let's consider a right tail test. Let's say that under the null hypothesis, we are given this value of mu sub 0, a known value. Now, if we look at this diagram and see here's the value of the observed statistic, and you see that that value is relatively close to the mu sub 0 under the null hypothesis. Because it's relatively close, very likely we will not reject the null hypothesis. And notice that the decision about the null hypothesis relies on the value that is proposed for the null hypothesis, mu sub 0. But now let's assume that we happen to know the mean under the alternative hypothesis, and that mean is mu sub 1. Well, you see that the observed value of the statistic is close to mu sub 1, so you may decide that actually mu sub 1 is a correct decision. That is, we reject the null hypothesis. But again, in practice, we never know what mu sub 1 is. So because of that reason, because the population mean is really never known, and when we decide to not reject the null hypothesis, for example, like what we're proposing here, then when you reject the null hypothesis, that doesn't mean that the mu sub 0 is the true mean of the population. We just don't know. We don't have enough evidence to contradict that, because the x observed is enough evidence to think that the mu sub 0 under the null hypothesis is correct. And for that reason, since we never know the truth, we're very careful in the language that we use. So we say that we failed to reject the null hypothesis, or that the null hypothesis is not rejected. We do not say we accepted the null hypothesis or we accepted the alternative hypothesis. We cannot say that because we don't know the true value of the parameter. So that's why we use failed to reject or the null hypothesis is not rejected. All right, so hopefully this clarifies the language that we use. The next concept is that of the, well, we already talked about it, but now I want to talk about how the significance level is used. So number one, the experimenter, the person performing the experiment, determines the significance level, the value of alpha. And that represents the acceptable risk of making the type 1 error. And this diagram is a diagram that we use for the example that we started with in Module 9. And we were asking if the observed value of the statistic was rare enough to decide that this mean is incorrect. Well, here's where we use the value of alpha. So the probability of making the type 1 error. So and from alpha, we determine a critical value. So this is the point from which we will start deciding that if we'll obtain a sample average that falls in that region, we will say that then we don't think that the mean is 1077. So you can compare the critical value with the value of the statistic and say, well, this value is to the right of this critical value, therefore I decide that this mean of 1077 is not the correct value. Another option is to compare the probability of obtaining this average or a larger value and compare that probability to alpha. So if the probability of obtaining this value is less than the probability of making the type 1 error, then we say that this mean is not the correct value. So this is how we use the significance level to make a decision. And I'm now going back to that example we started with. And you can see that we haven't established the value of alpha, so we can still not make a decision. But if alpha had this probability, then you will decide that this value of the mean, the sample mean, is enough evidence to say that the mean is not 1077. So in fact, I just illustrated the two approaches we use to decide about the null hypothesis. One approach is called the critical value, and that's where the critical value of the test statistic obtained from alpha, the significance level, is compared with the calculated value of the test statistic to make a decision about the null hypothesis. Another equivalent approach is that making the decision using the p-value, and that's where we compare the probability of the type 1 error with the probability of obtaining a value, or observed value, or a more extreme value of the test statistic under the assumption of the null hypothesis. And based on that, we make a decision. Now, before we can explain this more in detail, we need to talk about the test statistic. All right, so how do we select the probability distribution so that we know what test statistic to use? Well, remember, we're using the sample mean and the standard deviations that come from the sample. So we will use a t-distribution with n-1 degrees of freedom if the observations in the sample are independent, if the standard deviation of the sample replaces the standard deviation of the population, and the sampling distribution of the mean is normal. If these three conditions are met, then we are correct in using the probability distribution. And when we select the t distribution, then we know that we will use this test statistic. And we call it the observed value of the test statistic, or the calculated value of the test statistic, and we use this OBS to designate that this is a calculated value. So X bar OBS, that's the observed sample mean. Mu sub 0 is the value of the population mean under the null hypothesis. OBS is the standard deviation calculated from the sample, and S is N is a number of values in the sample. So all of these numbers are known from the problem that we're given. All right, so now that we know what test statistic we're going to use, we can talk about the two approaches to make a decision about the null hypothesis. So we will use the critical value T sub C that to distinguish where is the rejection region and where is the non-rejection region. This value of T sub C is found in table 5 using the degrees of freedom of the T distribution and the value of alpha. And then, but now where is that rejection region, even once we know this critical value, will depend on the direction of the test. And then if the calculated value of the test statistic lies in the rejection region, that means we will reject the null hypothesis. If it lies in the non-rejection region, well, that means we will not reject the null hypothesis. And these diagrams show you where the rejection region is. So if we have a left tail test, then the rejection region is to the left of the critical value. If we have a right tail test, then the rejection region is to the right of the critical value. And if we have a two-tail test, then we have two rejection regions. One to the left of the critical value, the positive critical value, and to the left of the negative value of the critical, or the negative critical value. And those are obtained by dividing the alpha by 2. Now, sometimes these critical values cannot be found on the table 5. So for that reason, I'm providing the formulas in Excel that you can use if you like to find the exact critical value. Now, in terms of the p-value approach, remember the definition of the p-value is that the probability of obtaining the observed value or a more extreme value of the test statistic under the assumption that the null hypothesis is correct. And the p-value then is found from the calculated value of the test statistic and from the direction, based on the direction of the test. But the decision about the null hypothesis is then that if the p-value is smaller than alpha, then we reject the null hypothesis. If the p-value is larger than alpha, we do not reject the null hypothesis. Again, I put this little mnemonic that some people find useful, and it says that if the p-value is low, the null hypothesis must go. All right, again, I don't know if that helps you, but it's there for you. All right, so how do we determine the p-value? Well, if you have a left tail test, then the probability to the left of the calculated value of the test statistic will be the p-value. Now, this t observed may not be in table 5 for the degrees of freedom that of the t distribution. And this is a very common occurrence because you remember table 5 shows you only 6 probabilities, if I remember correctly. So you may have to use the Excel formula to find the exact p-value, and I'm providing these formulas here. Now, if you have a right tail test, then the probability of that will be to the right of the p-value will be the probability to the right of the t observed value. And here's the formula for that. If you have a two-tail test, then the p-value is the probability on the left and the probability on the right. So we have to add those two probabilities, or you simply multiply the probability to the right of the observed, the positive value of the observed statistic. And here's a formula to find the exact p-value. All right, we'll stop here. And in the next section, we're going to start looking at problems where we apply all of this.